Like to introduce to you an idea called function notation. Function notation is another way to write a problem that we've seen in the past, but understanding that what we're looking at is defined as a function. In times past, we would look at an equation such as y equals 2x plus 3. We understood that the x represents the independent variable and y was the dependent variable because it depended on what x was. Well, when we look at functions, we're going to look at a similar idea, but we're going to write in terms of function notation. Where I'm going to write, rather than y, I'm going to write f of x equals the existing thing, 2x plus 3. So I'm asking us, what does x do in this function? What is the value of this function with x at a specific spot or a specific value? Now, function notation can look like, and it's read f of x. It can also be read as g of x or h of r or whatever you have, whatever you might have as you're looking at these. So typically, we're going to be asked to evaluate functions at specific spots in time or specific values. So for example, I might want to know what f of 4 is. What's the value of this function at 4? Well, how we determine that, we'll take our function, and everywhere I see x, I'll put in a 4. So I'll write f of 4, because number I chose, that'll be 2 times x plus 3. Everywhere I saw an x, I'm going to insert the value that I'm looking for. So what does this function do when x equals 4? We could solve that out, and that will equal 2 times 4 is 8. 8 plus 3 is 11. So f of 4 equals 11. Let's take g of x now, and let's evaluate that at another value. Let's choose negative 2. What does g of negative 2 look like? Well, everywhere in this function, I see an x. I'm going to insert a negative 2. Then solve that problem on down. 2 times negative 2 squared is 4. 2 times 4 minus 1, I changed pins on us. 2 times 4 is 8. 8 minus 1, that equals 7. So g of negative 2 equals 7. H of r, I want to look at, and let's say that h of r equals, and I want to find out what happens at negative 5. So h of negative 5. What I'll do now is I'll put negative 5 in everywhere there's an r. See if I can backwards put these things in there. And that's the entire negative 5. So negative 5 cubed minus 2r squared plus 5. I think I did it all right using multiple colors there. Negative 5 cubed minus 2 times negative 5 squared plus 5. So basically, I'm evaluating this function at a very specific location. And that location is identified as h as r being negative 5. Let's work this out. Negative 5 cubed is the entire negative 5 being cubed, and that becomes negative 125. Minus 2 times negative 5 squared. Negative 5 squared is 25. Times 2 is 50. Plus 5. Let me double check that. Negative 5, that's 25 times 2 is 50. Solve that down. 125 minus 50, that makes it 75. Or makes it 175 plus a 5 makes that a negative 170. And then we'd also see some functions that may look like this. Say f of x equals 2x plus 7. and I want to evaluate at f of, say, something like a plus h. How do we solve that? Everywhere we see an x, we'll include an a plus an h, and then continue with the problem. Work that out. That equals 2a plus 2h plus 7. So this function, whatever capital F the function is, f of a plus h equals 2a plus 2h plus 7. And I can't reduce that any further than that. Anyway, this is just a little bit of an example for you that you're going to see a lot of our equations, a lot of our models written in terms of a function. Mathematically, we're going to do the same work we've done before when it was y equals, but we're going to look at a very specific equations, ones that match up with the rules of being a function.